Hello, my precious subscribers and watchers. Both are precious, but I love subscribers more than just watchers. In just 2 minutes and a half, there will be start of the contest 819 Grimoire of Code annual contest. I don't know, Grimoire, something like that. I don't know. Oh, what it is? Ah, official competitive programming club of IIT Kharagpur. Who is the author? Ah, Indian. Limda. Who is a Limda? I don't know. I guess the contest is nice since it's given as paid contest, so it's both Div 1 and Div 2 for both divisions, so it must be really nice quality, or else it wouldn't be possible. Let's prepare some Microsoft Paint for our beautiful drawings. And the contest, okay, I'm running the recording. The contest is starting soon, just 1 minute. And it's longer than usual, so it's 135 minutes. It's because it's div 1 plus div 2. It has been a long time since the last Division 1 contest, so it's been, I don't know, like almost month, maybe three weeks. So I have to get used to contests. I hope it will be good. We just have to be fast for the easy problems, and we have to solve some hard problems. Then the contest is okay. Ah, I didn't make English. Sorry. A manic and array and positive integers. Pick a subsegment of this array and size cyclically rotated by any amount. Maniac wants to maximize the value of an minus a1 after exactly one such operation. So what he can do, he can rotate the whole array, or he can rotate everything but one element. So it's an easy problem actually. So first of all, we read n, then we find the maximum among the minimum. So we want to find maximum except the first element. And minimum except the last element. And also we want to find an minus an a1. So it is like element minus the next element. So G is like max of G, and Vi minus V sum I1n. And now we see out maximum of three numbers. of G, mn, so v back minus, sorry, max here also, mn minus, or mx minus v front, and minimum of, no, not minimum. Here we have to write v dot back minus mn. So this is it. Yeah, I think yes. Okay, let's run it. So 10, 0. Okay, it's good. Oh, it's my photos. Yeah, this is my photos. Great. Problem B. My index has two. I'm the first place. No, I'm 66th place. It's still okay, but not really. Sequence interesting if for all integers the bitwise XOR of all elements in A, which is strictly less than AI, is 0. So every element except the maximum is has even number of occurrences. It's obvious. Such that the sum of all the elements in the sequence A is equal to M. So we just take a lot of zeros and one maximum number, don't we? So why is it no? Where is it no? Ah, 2, 1. So what's the problem? Why 0, 1 is not an interesting sequence? Again, of n positive integers. I got it. Yeah, so we want to take a lot of ones and one element. Okay, so we want to take a lot of ones. So we read n and also we read m. So if m is at least n, then we can just take a lot of ones. And else we shout no. Okay, let's check. Yes, 3, yes, a lot of ones and 7. No, it's not true. We cannot have a lot of. We cannot have 5 ones, so we can have only 4 ones. Okay, so we take 4 ones. Uh, Interesting. What do we do? What do we do here? So let's assume that n is even. Let's assume that n is even. In this case, let's take the maximum and all the maximums. And the rest of the numbers, there should be even numbers. So, and n is even. So we have to have this number also even. Okay? We have to have this number also even. So we have to have two maxima. Okay, so let's take a lot of ones. For example, 6 ones, I don't know. And two equal numbers m and m. So what if they are, so what if this number is odd? If this number is odd, then we are in the trouble. Yeah, because this sum is even and this sum is also even. So m should be even. So if n is equal is divisible by 2, then m also has to be divisible by 2. Okay. Okay. So if m is at least n, and m should be divisible by 2. Okay. Or, I mean, m should be divisible by 2, or n should be not divisible by 2. Sorry for this loud sound. So we do this. We do this even number of times, of course. We do this even numbers of time, a number of times. So it should be n minus 1 minus uh, something like this. So this is always an even number. Let's do this. So if we take this u, we do this, and then we do this. So without this number divided by n minus u. Great. I think it's great. Yeah, I think it is excellent. So let's check this. Let's check this a bit. Okay, yes, 3, yes, a lot of ones, and 4, 4, no, yes, 1, 1, 4. It looks like this is true, but let me check a bit more. I want, okay, I want 7, 15, 7, 16, 8, 15, 8, 16. This is what I want. Oh, sorry for the noise again. So, okay, this both work. This works because it's 16, and this is impossible. Yeah, I think we are okay here. I think it's nice. Oh, great. But my place is awful. Okay, problem C. Fill the gifted Laman Babu a balanced bracket sequence S of length to n. Balanced sequence? Ah, okay. K, I, and J are connected if this subsegment is a balanced bracket sequence. Yeah. Undirected and unweighted. Determine the number of connected components in this graph. Nice problem, of course. Obviously, it's a nice problem. Okay, so first of all, uh, if two brackets are connected, then the balance is equal. So balance is like the difference between the number of opening and closing brackets before this symbol. They are equal. So if this is connected, it means that the balance is always positive between these two brackets. Okay, this is easier. This is quite easy. We should solve it now. Okay, we read n. We read the sequence. We read the sequence. We read the sequence. So we just track the answer. We just track the answer. It's like it's like 0 in the beginning, yeah. So if C, then we just if this is opening, we just increase our balance. And if it's closing, what we do then? We just increase the answer. That's all. And decrease the balance. Just like it. It's strange, but let's check. Oh, I didn't output anything. No, it's not true. Why it's not true? Because of this sequence, it should be 2. So this is the first. Ah, yeah. Yeah. So, for example, in this case, I can connect these two brackets even though this is closing, so we reduced our balance back to 0. So here we have only one connected component. Yeah. So when we close a bracket, when we increase the number of components, we do it when the previous bracket, no, yes, at least the previous bracket has to be closing. Yeah. So when two brackets are closing, yeah. if we have this, then we increase by 1. Yeah, because this cannot be connected anymore with. Okay, maybe it's true. Maybe it's true. Is it true that it is balanced? Yes, it's correct that it is balanced. I guess that's it. I guess that's it. But maybe it's wrong. Oh, it's correct. Great. Interesting problem. I didn't expect it to be so easy. You're given a connected, undirected, and unweighted graph with n vertices and m edges. Number of edges is at most n plus 2. Great. Let's say we color some edges red and the remaining edges blue. Now consider only the red edges and count the number of connected components in the graph. Components. Connected components. Let this value be C1. Similarly, count the number of connected components in the graph, in the blue graph. And this is C2. We want to assign the colors so that this quantity is minimized. Yeah. So let's look at any spanning tree. Yeah, so we have some spanning tree. We have some spanning tree, and we want to and we also have at most 3 additional edges. So let them be like this. No, let them be vertical. So we have a DFS graph and we have vertical edges. Great. So what do we know? We want to find the number, the assignment so that the quantity is minimized. Yeah. Uh, so the best for us if this is if the both graphs are acyclic. Yeah, because in this case we just have we have 2n minus m. This is the answer in the ideal world where the both graphs are acyclic. So is it possible to always make it acyclic? I think yes. So let's draw this graph as red and the remaining edges are blue. So if these blue edges form a triangle, then it's bad. Obviously, if they do not form a triangle, then we go on. So what if they form a triangle? Yeah, so we have a triangle and some tree. Some tree with this triangle. I don't know, something like this. Maybe we want to color this edge. Okay, let's make it this. We want to make this tree red, but add some edge here. Some red edge from the triangle, and instead give a blue edge. I mean, okay, the tree is red, yeah, and the triangle is blue, And this is bad because the blue graph is now, it has a cycle now. Yeah, in this case, we want to color one of these edges red and instead make some of these edges blue. Is it always okay? I think yes. For example, we take a triangle. Yeah, we take any of its neighbors. So yeah, we just take this path. We take any edge from this path, just absolutely any edge from this path. And we say that now this is blue and this is red. Yeah, we do not have cycles. Yeah, we just don't have cycles. And yet this path is not a cycle because now it's just a blue path. And this edge cannot be a triangle. So, okay. Yeah, really, it's okay. Let's try and do it. So it's always possible, and answer is always n plus m to n minus m. We read n m m. So first of all, we read the graph. Now we have to make a DFS. DFS in the vertex 0. Okay, we also want to have some parents. Yeah, I want parents and I want the color of the edge. Okay, it's like this. Let's fix it. Okay. we look at the neighbors. We look at the neighbors. And if the neighbor is not visited, if this is not visited, then we run DFS from this neighbor. Also, we say that v of p of v, p of this vertex is v, and also I want to find the number of edge. So the number of edge is like h, and then we run DFS of the same. Yes, I think it's okay. I think it's okay. Yeah. Yeah. So what do we do now? If we have a cycle, we want to take some of the vertices and fix something. So what is the cycle like? It's like we take. I think we want to have. We want to have also the heights of the vertices, so it gets harder. HH. We say here that HH of GVI is 1 plus HH of V. Excellent. So now we know all the heights. What do we do next? Next, we find this answer, this strange answer of length m. We start with the vertex 1, and we say that answer I equals. No, not answer I, answer PPI. Yeah, it's equal. It equals true. Now we look at all edges that are not colored. So if E, also let's keep track of the all vertices and the lowest vertex. So in this case, we do this. Not only do we do this, but also we want the lowest vertex and the number of edge with this lowest vertex. Oh, it's so hard. Sorry, it's so hard. So what do we do here? We take EI dot x, and this is the first endpoint. So we say if HH of this vertex is greater than HH of low, then they are then we just take low equals ei dot x and edge low equals I. And the same goes for the second endpoint. Great. And also we put them both into S. Great. So if E dot size is at most 3, at most 2, so it should be 3 exactly if we want to change something. And also if S dot size is also 3. In this case, everything is bad and we have to fix it because we have a cycle. So we take our lowest vertex, our lowest edge, and we make some swap. So we say that the lowest edge here, this lowest edge, it was false, but now it gets true. But see, if you have this vertical edge, and this is now red, you have a cycle because there is a path of 3 edges. So you have to take this edge and make it blue. And this edge is exactly pp of the lowest vertex. So we say that ans pp of the lowest vertex is false. And that's it. Now we just shout all the answer. Uh, I also have to print answer. I don't have to do it. Okay, let's check that we have the correct answer. Oh, we have to check it, I guess. I guess we have to check it. Okay, let's check it. So, the first 3 edges, first of all, we have this graph. We have 5 vertices. We have 7 edges. 1, 2, 2, 3, and 3, 4 should be. What's happening? I cannot tell. What's happening? Ah, some strange things happened. So these 3 edges should be red. Then we have. Ah, I hate it. What's happening? I don't want it. Then we have blue, red, and 2 blues. Blue, red, and 2 blues. 1, 3, and 3, 5 have 2 blues. Excellent. It worked. Now for this graph, we just say 1, 1, 0, 1. Correct. And finally, this graph. Ah, it's not finally. So what do we have here? So red, blue, 2 reds, blue, 2 reds. Two reds, blue, two reds. Okay, guess that's fine. And finally to 1, 1, 2. It should be correct. I think it should be correct. Not that bad problem, but it's a bit technical. I can't say that I hate it, but it's a bit technical. And okay. Ah, almost 1 second. 2 seconds. It's okay if we have 2 seconds. And I did it in time. Problem E. A permutation P is called almost perfect if for all. Oh, Krabarak is participating. For all integers, it holds that pi minus pi inversed is at most 1. Count the number of almost perfect permutations of length n modulo this. It's an interesting problem. Let's see. So so we know that for all I, pi, let me change this to some other color, for example black. For all I, pi minus first is at most 1. What do we know about it? We know that first of all, if pi is just I, then we are okay because this is 0. So let's assume that we have some cycle. Yeah, we have some long cycle. Then it is known that in this cycle, these two vertices should be of difference at most 1. So there are several cases. First of all, it can be like this. Yeah. Yes, it can be that like this. And in this case, these are just two any numbers. These are two any numbers. Secondly, we can have like this. Yeah. And these two numbers are adjacent, and also these two numbers are adjacent. Okay. And finally, also we can have something like this. We cannot have anything else because, for example, I mean, let's consider a cycle that's like this, but jumping two edges at once. So this will be cycle at length of length at least 3, and in this cycle we know that any two adjacent numbers are at most 1 in difference. And this is not true for just cycles which are long. For example, if you have at least triangle, you cannot have all three numbers. So this is difference at most 1, this difference is also at most 1, and this is at most 1. It's just impossible. So when you jump two edges at once, you can have a cycle of length at most 2. And this is possible only for cycles of length 1, 2, and 4. And if in case of 4, it should be like this. So the diagonals must be adjacent. Okay. Finally, we have to count it. We have to count it. We have to count it somehow. So first of all, we have to choose all these cycles and do something after that. So we have to choose all these cycles. Okay, let's assume that we chose k cycles. Let's assume that we chose k cycles. When we have done that, we have n minus 4k vertices. And what we have to do here is just divide them in the groups of 1 or 2. That's all. We have to group them like one or two. And how many ways of doing it? It's easy to count. You just say, let's take the last vertex. So we are counting fn. So maybe we just take this as a single group, fn minus 1. Or maybe we pair it up with something else. So this will be n minus 1 times fn minus 2. And this can be easily calculated in the linear time. Yeah, we are we are we okay with yes, 3 times 10 to the fifth power? We can just calculate this in the linear time. So we know fn, and all we have to do is to calculate the number of ways to make k cycles. So again, what do we do? Like gn. What is gn? First of all, we can pair n up with. We can just leave n and do not use it in these cycles. So this can be just gn minus 1. Or we can pair it with n minus 1. And in this case, we also have to choose some pair. We just have to choose some pairs and then pair them up. Okay? So, okay, I think we just have to write it. We have to write it and not spend time on writing it in Paint. We have to implement this. We just have a number n. We erase this DFS. First of all, we calculate the vector f, n plus 1. So this is how many ways of pairing n elements. So in the beginning it's 1. And we say that fi is sum of two numbers, fi minus first and product of two numbers, fi minus second and I minus first modulo m. Okay, this is the vector f. Now we have to calculate the number of ways of choosing k pairs from R. Okay, unfortunately there are two numbers here, so there are k and n. Okay, let's think. G, what is g and k? We can ignore n. First of all, is 2k should be here, but okay, l. N minus 2l plus, maybe we just take g n minus 2 l minus 1. So what is it? What is it? It's like some dynamics. It looks like a choosing number, but not really. It's like choice number, but not really. Ah, let's take h n l equals hxy, I think, and it equals g x minus y y. Okay, yes. So in this case, sorry, I have to increase some space. So what the identity we have? We have that hxy equals gx minus y, and this we know equals gx minus y plus gx minus y minus 1 here minus 2 y minus 1. And let's go back and apply this. So we have to add upper number to the lower number. So this is h y x minus 1 plus h. We have to add this number. Sorry, then we have to make a plus here. Yeah, we have a plus here. So again, plus, plus, plus. And now we just now, instead we do find the difference. We subtract the y. So x minus 1 y, and here we have x minus 1 y minus 1. And this is just the choice number. Okay, this is just the choice number. We also have to find the starting conditions. We have to find the starting conditions, but I guess it's just one. Okay. So just, for example, I want to find out what is h. What is h x x? Yes, what is h x x? Yeah, it's like g to xx. So how many ways are there to make x pairs from two x elements? It's just 2x. Yeah, so I guess we understand each other. And this is the answer. So, okay. So this is just this choice number. What we do next is, so again, we know that G and L is C choice number. I can write it like an American. Says N minus L over L. Okay. Now, now, now when we know this, when we know this number, we just iterate. So we choose k from 0 to n halved. No, I mean, n a halved, it should be n over 4. And for this k, L is equal 2 times k. Then, what do we do then? Then we say that this is uns. We count uns. So we have to find this number of ways. First of all, we choose L pairs, and we can do it this number of ways. So prod of factorial of n minus L and product of inverse factorial of L and inverse factorial n minus 2 times L modulo m modulo m. We have to find these factorials. Like great. We found all factorials and inverse factorials, and now we found number of ways of choosing 2k pairs. Secondly, we have to pair these pairs up. So this is pairs. Then we have to pair up them. And this is this thing. We have to say like it's just double factorial, you know? For example, if you have, so it's like 2k minus 1 times 2k minus 3 times etc. times 1. Okay, let's calculate double factorials. So dfact of I equals product of I and dfact I minus 2 modulo m. So here we have dfact, we have just dfact of L minus 1. And we take product of pairs and this dfact modulo m. Also, not only that, but actually, not only that, we also have to kind of, in each cycle, for example, we have a pair 1, 2, and 3, 4. Yeah, there are two ways of pairing them up because we can do it this way and we can do it the other way. So we also have to multiply it by 2 to the power of k. Okay, it's easier. Sorry, something random is happening. So P2 of I equals sum of P2 I minus 1, P2 I minus 1 modulo m. So here we also multiply it by P2 of k. What's next? After we have made up all the 4 cycles, we have to add the f. So it's product of n square prime and f n minus 2 times L modulo M. And in the end, we just add this to the sum. And we output the answer. Ah, great. It is great. But the answer is not great. I dislike it. The answer is not great. Why? Why isn't it great? What happened? So like, what's wrong? So first of all, K, so N, we at least we have to make this, okay? So L, so K is, this is release, sorry. We have to do it in debug. So we know that L is 0, layers is what's wrong? L is 0. L is 0. Two, 4, and correct answer. Okay, okay, we're doing good. We're doing good. Okay, mathematics works. Finally, mathematics works. But Tromax is he's beating us. Oh, red color and green color. These guys are really fast. See, this guy spent 35 minutes and I spent a whole hour. Is it okay? Is it okay for these guys? Oh man. How is this even happening? Okay. Dibiotic has a very important meeting to attend and he is already very late. There was some announcement. Okay. And tourists spent half an hour, okay. Each traffic light cycles up to 2 seconds. The ith traffic light is green for the first GI seconds and red for the remaining T minus GI seconds. Something like dynamic programming. Okay, dynamic programming. Some dynamic programming. Why are these guys so fast? I don't understand it. Why are these guys so fast? Can someone explain me? Something incredible. So let's look at this function. We have several traffic lights. So, I mean, we have t moments of time. Yeah, I mean, t residues modular t. Yeah. And while we have these t residues, we have some edges. What are the edges? We can move from some traffic light to the next traffic light. In some amount of time. First of all, let's assume that, okay, traveling from the light to the next light is just something extra in this, redundant. Let's just reduce this number by, I mean, d something, and let's assume that actually all the traffic lights are in the same point. Okay, and in the end we will have to add this number to the answer, of course. So we know that all traffic lights are in the same point, and moreover, so this is just, there are several, we have a circle of length t, and we have several segments which are prohibited. Yeah, there are several segments which are prohibited, and if we step on a prohibited point, we have to move all the way to the end of the prohibited segment. And our goal is to find the starting point from which our path is minimal. So first of all, if you have, yeah, we have several segments and we just jump to the end of a segment if this is a bad segment. Okay. So we know that this is some function. Yeah, for each point we know what is the waiting time. Assume that we add some segment in the beginning. Yeah, we add some S segment to the beginning. So what happens in this case? In this case, all these numbers stay the same. Yeah, and these numbers change. So this number is +1 of to this number. Yeah. So this number is spread here. This is +1, this is +2, and this is plus n, something like this. Okay. Mm-hmm. So let's consider the second circle in which we have these numbers. So like this is circle x, and we have here yi equals xi plus I. Yeah. In this case, for example, let's take 3 steps. Yeah. Here should be xi minus third. Yeah. And we know that xi minus third equals 3 plus xi. But since we added this I, we have xi minus 3 plus, it should be plus 3, plus I minus 3. So it is just xi plus I. So this is like adding on a segment, okay? This is a segment tree with adding on a segment. Oh, not with adding on a segment, with assignment on the segment, okay? So the only thing that we have to do is to make sure that we can assign on some segments. That's all. All we have to do is to assign on a segment. All we have to do is to not only have to do it, but also we have to find a minimum. So we have to find a minimum in this whole segment tree. It's something like implicit segment tree, I think. Let's try and do it. I think it's okay. It shouldn't be very bad. So int n and t, we read them, and then we read these numbers, g and c. So as I said, we have to, this will be done in the end. Okay, in this case, let's just do it in arrays. Green light, red light. So we read D, add it to D, And after that, we say that actually G and C should be reduced. So the ith light is Ci seconds into its cycle. Yeah, it's already 2 seconds. But when we come to it, it's already, for example, 4 seconds. If we spend these d seconds to come to it, it is already 4 seconds. Yeah. Therefore, we just add this number d to both to c. Yeah, and g is not affected. G is not affected. So just c equals sum of c and ci. Ci and d modulo t. Okay, that's very nice. And now we have to make a series of adding on a segment. Or not adding on a segment, but like assignment on a segment. Okay, so in the beginning we have an array of zeros. We have an array of zeros, and actually, in terms of this segment tree, it's like, so as I said, we have I erase it. So we have changed all times t prime I equals ti plus I. Yeah. Yes. Ti plus I. So we store not this array but this array 0, 1, 2, etc. n minus 1. Let's do it in our strange segment tree. Yeah. So it is like storing an arithmetic progression. Yes. Okay. So we store. First of all, I think we have to make this number static. And let's store this in T. So we go from the end to the beginning. Sorry, I'm thinking. So segment tree ST. Sorry. Oh, yes. Yes. So we're doing it. Segment 3. And initially it's a sequence of from 0 to 0, and it is increasing. Okay. So we say here that it should be enough, I think. No, this this is a bad idea. Segment 3. So we just store this beginning and bool b. Also, sometimes we store. Okay, let's make it shorter. Okay, we made it. And by default, L and R are just like A and B. So let's write their destructor because it might be helpful. And if L, then we destroy it. If R, then destroy it. That's it. Next we have to perform the separations. So what is the separations? Are the separations like? First of all, we have to find an element. Find element. It's Fe, and we take the position, and we take this PIIP, which will be explained later. So if L So first of all, we have to find whether either this is in the left part or in the right part. Okay. So if int m is px plus py halved. So if pos is less than m, then we are interested in the left part. So if L return L find element on pos and PIIPXM, else return A plus, else if B return A plus pos minus PX, else return A. Else if R return R find element, else if B return this, else return this. Excellent. Okay. Okay, we have written this function. Next, we have to make an assignment. So this is like void assign. And what we have int L, int R, and PEE. Also LL value and PII P. Okay. So first of all, if we are fully contained in the segment LR, then we just change it. So okay, yes, if L is at most p dot x and R is at least p dot y, then we are just contained in this large segment. What do we do then? We say that we have to destruct ourselves, and we say that A equals val and B equals false. So, okay, else we just do it with our both children, okay? So if not L, then L is new segment tree of A and B. Ah, no, it should be PIP. And if not R, R is new segment tree of A A plus M minus PX B. Ah, if B, then this, else just R equals new segment tree of A and B. So in this case, we create everything and we just call for the both children. So we say assign LR LR val PIP.xm, and we assign the same from M to PY. Yes, sounds solid. Sounds solid. This sounds solid. Okay. 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 What's next? So we just have to apply these operations. That's it. I think that's it. So we take a segment which starts in point CI and lasts GI seconds. Okay. So GI is what? What is GI? GI is green. Okay. So it's like it is read from CI plus GI ending with CI. So this is red light, and we want to assign. First of all, we have to take the point CI. This is CI, as I said. We have to point. We have to take the point CI, and maybe find the value. So llval equals st dot find element on position CI. Okay, let's just find L equals some CIGI modulo M, and R is just CI. And we find element R for P. Secondly, so if L is less than R, then we just make the assignment. From L to R, value P. Else, there is something more interesting, because we make assignment from 0 to R of this value, but also we make an assignment from L to T of value also plus T modulo T for P. That's it. That's it. Let's check it. I think it's something awful, but and that's sad that it is awful. So what's the problem? In destruction failed. So L is not 0. Okay, how did this happen? How did this happen? Oh, I hate it when all these strange things with pointers happen. Okay, let's investigate it. So we have 0, 0, 0, 0, 10. And now L and R are both null pointers. So we create them. Yes, we just create some segment trees. And we assign here and assign here, and assign here, and now we have destructed it. Why did I understood it. So we have to make them zeros. Oh no, again. Stack Overflow? Why? Why? 0, 1. So, ah, got it. Okay. First of all, if R is less than P, or L is at least Y, then we don't do anything. Okay, this is our error. So, but we didn't have any output. In the end, we have to find the minimum. So let's just output the minimum. This should be easy. So first of all, if L no, I don't need a minimum. I need a minimum except this uh, uh, except this arithmetic progression. So actually it's not that I have to find minimum minus I. Okay, I have to find a minimum minus I. So if first of all, if L and R, and we know then they are both, then are there, then we just int m equals this, and we say that we return minimum of these two numbers, lmn of pii p.xm and rmn pii m p.y. What's wrong? Are you okay? Great. Secondly, if b, then it's just increasing and we just output any number. Else, we say that we output a minus py minus 1. 11. Oh, whoa, 11. 16? Oh no, this is wrong. This is damn wrong. It shouldn't be 16, it should be 3. Why is it 6? Why is it 16? 16? Okay, second example. Let's look at it. Let's look at it. Strange. So he should arrive after 1 second. I mean, what? These all are zeros. Okay. So why is one? Why did it happen? Okay, let slow it down a bit. I think let's do it minus I. Okay. Okay, let's look. No, no, this is wrong. This is wrong. Why did this happen? This happened. What? Sorry, I don't understand something. Maybe I should have done also this. Why? Why is it so strange? Ah, this is wrong. It shouldn't be negative. It shouldn't be negative. Why is it negative? It mustn't be negative. Okay, let's take a look. So value is 6. Why is value 6? Ah, because it's increasing. Okay, let's not. Uh, it will be more comfortable if you don't do it. Okay, so let's just look at what is there in the array. So it's 6, always 6, and this is not good because it shouldn't be always 6. It should be sometimes 0. So L is greater than R. Ah, modulo M. It should be modulo not M. Sorry, it was my bad. It's still something wrong. Okay, again, let's come and look. L is 3 and R is 6. So L is 3 and R is 6. So we make an assignment from 3 to 6. Yes? G and C. And C is the starting point. So it starts from 3 and no, it starts from why? CI is we start from the end. So this is 6 6. This is 6 6. So this starts in moment 3 and ends in moment 6. Okay. Okay, I believe. I believe it. But I don't believe that this should be all sixes here. This is not true. So we create two children. Yeah. So now we have L and R. And they are like this. Okay, so after that, it should be like this. Of course, it should be like this. Sorry, guys. This is. Oh my. Do I have time after all? I have a lot of time. Yeah. It's two now. Of course, it's two. Of course, it's two. Why is it two? 9876. I don't understand a single thing. What's happening? So again, I made an assignment from 3 to 6. What it is like? Okay, so I have to make an assignment from 3 to 6. So I don't understand why these two numbers are both 6. So I just like these 2 and 3. They shouldn't be both 6. Yeah? Yes. They shouldn't both be 3 and 6. So for example, here, this is from 3 to 6, but B is 2, 3, and A is 2. So this should be just number 2. That's all. This must be number 2. Okay? This must be number 2. So let's look at the number 2. So position number 2. We go here. We go here. Oh man! Why are these bugs keep happening? Bugs. Okay, let's just look at all PII in this area because I hate it. Okay, this is okay. Okay, okay, okay. This is this is okay. Now this is again 2, but at least 3, 4, 5, 6. Okay. Okay, for example, in this case, you have to wait till this number. Yes. 5, 4, 3, 2. So let's start. When do we start? So why are there 2 seconds? I don't understand. 5, 4, 3, 2. So we can start here and do it in 2 seconds for some reason. I am asking why we're doing it. Yes, I'm asking why we are doing it. So in the beginning, so we are saying that I am saying that I can stop here. So I can start at number 4. Yeah, number 4. Let's try starting at number 4. Okay. So now this is number 4, and this is green light for this number. Yeah? But this is not green light for this number. So this number, when the green light is started, the green light starts at number 5. Okay, if we have a number 4, okay, we start at number 4, so we have 7, 0, 4, 3, 2, 1. This is what we have at moment 4. So I say that initially we wait for 2 seconds because this is a red light. Okay, this is a red light. So now we have 9, 2, 6, 5, 4, 3. Okay, so we have waited for 2 seconds, but now we are here. Sorry. This is very hard representation for my problem, so I cannot understand simply what's going on. Again, we're saying that this is the proper moment to start. This is the proper moment to start. 6. 6. So 6 is the proper moment to start. Okay, let's investigate this. So we have 6. Why is this the proper moment to start? I didn't get it, really. So first of all, we don't wait for any seconds. For some reason, we don't wait. Why don't we wait? Because this is 9. This is 9, it means 0. Okay, we don't wait this traffic sign. So this is still 8. Okay. We don't wait this traffic sign because I don't want this window. Because this green light is for 5 seconds. Yes, this green light is for 5 seconds. Okay. Now we come here, and this green light is for 7 seconds, and now we have 6. So it's okay. Here we have to wait. Yeah, here we have to wait for a lot. We have to wait here for 4 seconds. So operation 1, operation 2, operation 3, operation 4 is wrong. What happened here? So this is before this operation, this is before this operation, this is before this operation. So this 7 turned into this 8. For some reason, I said that it only needs 2 seconds. Maybe my solution is wrong. Sorry. No, my solution is not wrong. My solution is correct. But I spend so much time on this dumb problem. I must solve it. I must solve it. So here we have this 8. So again, this light is red. Okay. So what this 8 means? This 8 means that this segment went 8 points to the left. Okay. This segment went 8 points to the left. Didn't it? So maybe no, D is correct. So maybe I have to make minus ci. Maybe we have to take minus ci. Now it's 3. It is okay. And it says that we just... Yes, it's correct now. Let's remove... Also, I want to do this. And see... 1? Oh no, it's not 1. It's incorrect. Okay, in the first example, he said that he can just start at the first moment, but it is wrong. Yeah, this is wrong. This is wrong. We can't start at the first at the first moment. Okay, maybe we just have to do it. So in this case, 8 0. What is 8 0? I forgot to add 1, 2, 3, and 4. I forgot to add 1, 2, 3, and 4. And besides, this is correct. Also, okay. And actually, we have to start at the moment 1. Yes. Yes. Let's remove this and this. So this is 11. This is 3. And I try to submit this problem. Oh no, wrong. This is not good. Okay, let's... I don't know. First of all, I have to check that I don't have any problems with integers. So let's check for integers. So int pos, int m, okay, lr, okay, m, okay, m, okay, okay. Okay, no problems with integers, I guess. No problems at all. So is this correct? Again, what are these CIs? These CIs are just what light is there on the ith lights. What moment? So when we spent d seconds, it is added. Mm-hmm. Yes, this is correct. Okay, what about, let's check, let's check that I understand it for one light. For example, one traffic light and cycle length is 100. For example, 10, I don't know. And I have green light for 1 second, starting from 0. Okay, let's take 4. Excellent. And what about I have a 1 second green light starting with in 7 and then a green light starting in 6. It says 11. Ah, I also have to add number, for example, 6, 11. So if it is 0, it's also, it's 1, it's 1. Okay, what is the problem? Maybe I didn't use some modular operations where I had to do it. What's happening here? Why is this? Ah, okay. So if the array is constant, I just take the rightmost point, which is by minus 1. And I erase by minus 1. Yes. Yes, I do. But if this is increasing, then I just have to... Ah, this is not a minus px, it's just a. Yes? It's just a because because of how I do it. Yeah, I just put, okay, let's fix. I just say the number which is not in the beginning of the array, which is in the point 0. Okay, I have to put the number in the point 0. So we have to fix it, and this will be great. For example, in this case, this will be hard to fix, but we have to do it fast. Okay, this is just a plus pos. Yes, this is just a plus pos. Next. So and here we have also just a plus pos. Yes. Okay, here we have an assignment. We have to assign a value. So this is correct, yes. Okay, in case of assignment, we do everything right. Okay, create. Okay, in case of creation, we do not do everything right because we have to do this. Okay, so it's just A and B, nothing else. Okay, now we find a minimum. When we find a minimum, if this is increasing, yes, we do this and we do this. This is correct. Okay, if this is increasing, I erase bx. And if this is constant, yes, 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 this is correct. This should be correct. 1, why 1? Okay, let's just put this test and test again. 11, and it should be 3. Let's try it. Again, I take just the 0th element. If b is true, I just have to check all. I have to check all the places, yeah. But it is so hard. Okay, I now find an element. Yes, I try to find the element. If b, yes, I take a plus pos always. A plus pos. So I always make just new segment tree AB. Yes. I always just do segment 3AB. Yes, yes. Hmm. This is frustrating. This is frustrating. Okay, let's look at the third test. I think let's look at the third test, if it's possible. This is such an easy problem. Why didn't I solve it? So see, there are not that many guys with pretest 3. Usually there are pretest 6, 7, and like this. It's a shame. It's it's shame. It is a shame. Яхар Дубовик. Guys, do you see me? I suck. This is a catastrophe. This is just I was demolished. This is such an easy problem, and I wrote the full code for it. Why did it fail? Guys, why did it fail? I even cannot see the third test. Already an editorial? Oh no, there shouldn't be any editorial. F is shit. Oh, this guy has a point. This guy has a strong point. I liked the problem F. It is very technical again, but still, it is a bit nice. It is a bit nice. The problem is I didn't solve it. I actually solved it, but I didn't send the solution. Is this rated for div 2? Div 2. Ah, I now can see the solution. Maybe I can see tests. Can I see tests? Why cannot I see the test? I want to see the third test. Term Max is going to be the legendary Grandmaster. Because he just solved G. He just solved G. And almost solved E. F. I mean F. Ah, Bank made a hack. So he won Tourist. He defeated Tourist. Guys. Bank defeated Tourist. A bench. Maybe bench. Oh man. See, nikgaevoy is so slow. So we have only something like 400 of 100 difference. 400 difference. If I solve this problem, let's assume it's plus 1000, I would be something like here. Guys. Why did it happen? Okay, let's make some stress testing. Let's perform some stress testing. It's already convenient for stressing. Oh, I like it. I like it where you do this. It is actually quite nice. Okay, let's try it doing in this paradigm. Okay, so we make something like void solve wrong. Also, we have this. Okay, what we are doing now is we're trying to stress test our solution with nikgaevoy. So let's do this. In another main, we just say another solve wrong uh, of this. And let's move it here. And instead of solving wrong, we're trying to do another main. Okay, what do we do in another main? Solve wrong. What is solve test? Solve test. Okay. We have to check again. So let's make some tests. Let's make some tests. How do we do some random tests? Let's make some tests. Okay, let's take N and T. Make some random numbers. Okay, let's just make some random numbers. Nikgaevoy is saying that it is bad decision to use segment tree in this problem. What's wrong? I think this is because this uses some new standard. What is it? Ah. nikgaevoy likes new standard of C++, and this is okay, but for some reason I don't have these ranges. Thing. It's strange because I also have C++ 20 standard, but it didn't work. What is it? 3 plus 0? What? What is this plus 0? Ah, this is in the out. Okay, fail this test. What? Maybe I should make something like this in my solutions too, for stressing. What? Ah, guys. Guys, this is awful. Guys. Why didn't I do it? It's so obvious. Again, some failure. Ah, this is because of this. Okay, let's just make a line break. Why? Why did I do it? And still there is some failure. Okay. Failure is okay. Failure is okay. We have some other problem in our solution. Okay, for now, let's just make it 0. For now, let it make 0. So this is some sort of problematic test. Let it make not, for example, let's try 1. Oh, I also have problems with 1. Solve -5, stress 0. So I gave -5. It's really sad if you think about it. It's really sad. Why did it say -5? Okay, let's look. Let's investigate. Let's investigate. So it gave just -5 for some stupid reason. Let's look. So now ans is 0. It's correct. No, it's not correct because I also have to... I don't have to do anything. Yeah. So it said that from L to R, I make some changes. So I make an assignment of val on this segment. Why 0? Why do I do it 0? Okay, this is correct, but why? Why did this happen? So in several points, it became just became 10, for example. Okay, let's look at these numbers. These numbers 10 minus, okay, something like 9. Okay, here I take 0 minus So I didn't have to do this. I didn't have to do this. How does this keep happening to me? Another one stupid bug. So now I have 0. Okay, let's continue stressing. Guys, let's continue stressing. Maybe at some moment. Ah, stress -1. Okay, I think we see a wrong answer from nikgaevoy solution. Let's take, for example, n equals 2. Okay, I think Nikita Gavoy will be sad about it, because it obviously means that he will fail system testing. So Nikita has an error in his solution, as I have. So let's make 2 in again. Maybe he will not fail if n equals 2. Can I submit code? No, I cannot submit code. So now we not only fix my solution, but also fix Nikita's solution in order to continue our stress testing. How? Okay. So we want to continue. Yeah. Okay, so Nikita didn't solve F, but still I'm very sad because first of all, what I wanted is to solve F myself, and I didn't do it. Second of all, I don't mind if Nikita solves F, so it's not fair if he loses his F because only of a little bug. Okay, now we are again have some problems. Let's think who is right and who is wrong. Okay, we have two lights, and first one works for 2 seconds, starting with 1. So this is green for 2 seconds. This is green for 2 seconds. And first of all, it's 1. Okay. He also says to do this. Okay, since it's system testing now, I think I will just make an editorial of all problems. Yeah, I will just explain all the problems, and then we will try to upsolve problem G. So problem A is not a really hard problem. You can pick a subsegment of this array and cyclically rotate it by any amount. And he wants to maximize this number after exactly one such operation. First of all, obviously he can make the array the same as it was in the beginning. He can make it the same. So if he doesn't want to change it, he can leave it the same. For example, he can just choose this subsegment and do it exactly L times, where L is the length of this subsegment. I mean, as you see here, you can just take k equals r minus L plus 1, so the length of this array. So you just make the whole cycle, and the array is the same as it was in the beginning. In the beginning. So what's next? Our goal is to find our goal is to find the maximum possible number of an minus a1. Okay, what is it? First of all, let's consider three cases. Yeah, you touched this element. You touched this element. By touched, I mean you changed it, maybe. So it is in the segment that we are rotating. So first case is we changed. I mean touched an to, but not a1. Second is touched a1 but not an. And the third case, you touched both elements. So how are these cases solved? They are solved in different ways. In this case, obviously what you have to do is and fourth case is did not touch anything. Okay. So in the first case, you don't touch an, but you take some segment with a1 and you rotate it. So actually you can put any number here from this segment. And if we want to maximize an minus a1, we want to take a1 as little as possible. So we just take the minimum in this segment. And actually we can take the whole array except an and take minimum from this array. So in the first case, the answer is an minus minimum from a1 to an minus 1. In the second case, you touched. Oh, sorry. It is the second case. You touched a1 but not an. Let's solve first case. As in the previous case, you don't touch a1, but you take some segment with an, and obviously you want to take as big number an as possible. So you just take maximum in array from 2 to an and subtract a1. In the third case, let's just look at this array as at a circle. A circle. Yeah. So if we consider it a circle, then you just take a number and subtract it from the previous number. So an is just like a0 for a1. So you take a0 minus a1. So if we rotate this array, we actually can take any AI and subtract the next number. So we have to do it for all numbers I, including n. So maximum of ai minus ai plus 1 for I equals 1 to n. And again, if I equals n, then it is just an minus a1 of for I equals n. And in the fourth case, it's just like any of these three because, as I said, for example, in the third case, you can just rotate it n times. So this a n minus a1 is just here. So we don't have to consider the fourth case because we already considered the third case. Okay, and that's it for the problem A. As you see, I just did what made the most sense. Yeah, so Mn is the minimum except the last element. Mx is the maximum except the first element. And G is just uh, element minus the next element for it is the maximum for these differences among all i's. And I just say G or maybe Mx minus the first element or maybe last element minus Mn and maximum of these three possibilities. Nothing special so far. Problem B. Oh, this is quite interesting problem. Maybe you don't see this part of the screen because there is my beautiful face. Yeah, there is my beautiful face, isn't it? Ah, actually, you see something. Okay, so, okay, I will try to do everything in this area. In this problem, you take an array A and you say that for all AI in this array, let's consider all numbers B from A such that B is less than AI, and you want so you take this subsequence and you want XOR of this subsequence equals 0. So first of all, let's take the minimum possible element. First of all, let's sort the array A so that A1 is at most AB is at most A1, A2, A3, etc. AN. So this is sorted. Uh, let's take A1. As you see, the XOR is already 0 for all elements that are less than A1 because there are no elements less than A1. So this is already working. Let's take the second minimum except A1. So, I mean, there are several elements that are equal to A1. Let's take the next element after that. So if we take this element, then the XOR of all elements less than AK plus 1 equals 0. This means that A1 plus A2, this plus is XOR plus. XOR, I mean, just XOR. This should be 0. But as you know, this is like 0 if K is even and A1 if K is odd. Okay, because if K is even, then you can just pair up all these numbers and you get 0. And if K is odd, then there is one left here. That said, you have to have this K an even number. And actually, if you continue this uh, reasoning, you get the following. All numbers except the maximum one should appear even number of times. For example, minimum appears even number of times. The next number also appears even number of times, etc. And the maximum number may be appearing odd number of times. This is this is the statement. So this is when the sequence is interesting. So you want to find any interesting sequence with sum equal to m, okay, and with positive numbers. So uh, first of all, let's try using ones. Okay, so I want to put a lot of ones, and at the end I take m minus 1. That's it. Does it work? Actually, not always. Yeah, because I want minimum to be even number of times. So I want it's not m minus 1, it's m minus n minus 1. So I want it to be an even number. Yeah, because if it is an odd number, then this condition is not satisfied, and we are not okay with that. So we want this number to be even. So we want n minus 1 to be even. So this solution works if n is odd. So what do we do if n is even? The good idea is to try take uh, n minus 2 ones. Okay, so we cannot just take m minus n minus 2 because then you have n minus 1 numbers and you want n numbers. So in this case, let's just try take this halved. So I take m minus n minus 2 halved, and again m minus n minus 2 halved. And this only works when this number is whole number, when this is an integer. Because if it is not an integer, then the solution is obviously not satisfied. Okay, the solution is obviously not satisfied. Not solution, condition. So if this is an even number, then it works. So we take, so if n is even and m is even, then it is ok. We take n minus 2 once and these two numbers after that. This is okay. But what if it is wrong? So what if 2n is even but m is odd? Then we have a problem. Because look, as I said, all numbers except the maximum have even number of occurrences, except the maximum. But since the entire sequence has even length, the maximum number has also even number of occurrences. Yeah, for example, so let A be number of not maximums, and B is number of maximums. So the as you know, A plus B is n, and as we know, it is even. But also we know that A is even. Thus, we know that B has to be even. So as you see, maximum is also, it also has even number of occurrences, but that means that the sum is even because you can just divide all numbers into pairs of equal numbers, and in each pair the sum is even, so the whole sum is also even. So m also has to be an even number, and this is a problem because, as I said, we are considering the case where m is an odd number. So 2 divides n and 2 does not divide m is impossible. And you just output the answer after that. I hope that's okay. And we go to problem C. Oh, it's me. Do you see me? Okay, let's hide me. No, why did I open the problem D? Now C. Ah, bracket sequence. It's somehow strange problem. As I said during the contest, uh, okay, Nikita is asking to look into the standings and check whether his solution fails or not. Okay, this passed the tests. This passed the tests. Oh man. As I showed you, this solution is entirely wrong, but it just passed the tests. How is that even possible? How is that even possible? Oh, sorry. It was an accident. Not really good tests. I don't know. Okay, let's check tourist solution. I think tourist has the correct solution. I hope so. Hopes tourist has a correct solution. Okay. Why isn't tourist solution outputting anything? What's happening? Again? Sorry, what? The solution just ignores our input. Okay, let's try someone else. Let's try someone else. Maybe bank? Why isn't it working? Okay, let's try uphacking nikgaevoy. I really need it. I really need it. Okay. Now I can submit my own code and check if it is correct or not. Okay, let's continue with problem C, and we will. And no, we will not. Until I see that it is okay, we will not do it. And I will try to hack it now. I will try to hack it with this test, with the same test. So the correct answer is 2 here, okay? True max is not correct in problem G. So I think this contest is not prepared really well. You see, there are a lot of some strange hacks in all sorts of problems. It's not cool. It's not cool. Let's try to hack someone else. Okay. So problem C. In problem C, we have several pairs of moments, and in each pair of moments, we have the same balance on prefixes. For example, these two brackets are neighbors in this graph because in both cases, so in this subsequence and in this subsequence, the balance in the sequence is 0. That's why they are connected. But it's not the only necessary condition. The second necessary condition is that between these two balances, there shouldn't be negative balances. For example, if there were a closing bracket right after this one, then uh, we will we would have a negative balance, and this is not possible in this case. So we have to find a number of pairs. We have to find number of pairs. No, we want to find the number of connected components. So, for example, if you have two moments with the balance 2, we want to find out whether they are connected or not. This is easy to find out. If you have balance 1 between these two moments, for example, like this. No, balance 0. Balance 0. For example, like this. Then you cannot connect these two brackets because you have a negative balance in this subsequence, and you cannot take it as a balance bracket sequence. So, what did I do to solve this problem? I just said that this only happens. So, we want to do the following. Each time we have a too little balance, this means that we have a new connected component. For example, in this moment, there were only uh, two connected components, this one and this one. But if I add another closing bracket, then these two balances, these are both balances too, but they get disconnected because of this. And thus, And thus these are two. This is plus one to the answer. So we do this. And actually, the criterion is as following: we have to increase the answer if and only if there are two closing brackets in a row. So if you have something like this, then you don't have a new connected component each time because all these brackets have the equal balance, and we do not go into the negative balances. But if you have another closing bracket, then even if you then open it again and have a lot of brackets, this pair and this pair are now disconnected because of this thing. And actually, this thing is it can be found just by looking at these two closing brackets in a row. So each time I see two closing brackets in a row, I have to increase my answer. That's all. And actually, the solution only works if the initial answer is 1. In this case, it works. Okay, let's go to problem D. You have a graph, and this graph is almost a tree. So if there were, it is connected and directed and unweighted, and if there were n minus 1 edges, then it would be a tree. But actually, you have m at most n plus 2. So it is a tree with possibly 3 new edges, maybe 2, maybe 1, maybe 0 new edges. And we want to color all these edges so that the total number of red connected components and blue connected components is minimized. They state that this number cannot be less than 2n minus m. So, what I mean, if you have 0 edges, then you have 2n components because you have n red components because there are no edges, and you have n blue components because there are no edges. And actually, each time you add an edge, you can either make these numbers the same or decrease it by 1. Actually, this is not possible because the first step always decreases the number of components, but sometimes it is possible to make it the same. For example, if you have this red component and you add this edge, then the number of components remains the same because you connected two vertices that are already connected by red edges. So actually, the answer is at least 2n minus m because there are m edges and 2n vertices. But sometimes it can be, and we want to make it exactly this number. So we don't want it to be greater than 2n minus m. We want to minimize this number. And in order to do this, we want the red graph be the tree and the blue graph be the tree. Because if there are cycles, then there was a moment when we didn't decrease this number, and it would be greater than 2n minus m. How to make these both graphs two trees? First of all, you take any spanning tree and say that it is a red tree. Then you see at blue edges, look at blue edges, and there are at most 3 blue edges. If they are all if there are at most 2 edges, then they obviously do not make a cycle. So you just output this answer. Also, if there are 3 edges but they do not form a cycle, for example, something like this, 1, 2, 3, or something like this, 1, 2, 3. If they do not make a cycle, then also you can output the answer. The problem is in the case when you have a triangle. And to fix this test, to fix this case, first of all, I consider not any spanning tree, but only DFS spanning tree. And it is so-called normal tree, and it means that all blue edges are vertical. So, for example, this is not possible because this blue edge does not uh, it does not join two vertices that are vertical, so they are not ancestor of each other. They have some other common ancestor, and we are not okay with that. We are considering only a DFS tree, and in it, all blue edges are vertical like this. So in this case, we are trying to replace this blue edge with some other edge. For example, with this one. We just take the lowest vertex among these triangle vertices, and you take this edge. You say that this is new blue edge, and this is new red edge. And actually, there is a theorem that if you replace any edge in a triangle with any other edge, then it is not anymore a triangle. It is easy to prove. And as you see, we just changed uh, these two edges, and the only goal was to make the new red tree again a tree. So for example, it is always possible to screw it up. You have this path, for example, and you remove this edge, and you add this edge. Now you don't have a tree, you have a cycle. So this is not good for us. But if we do it like this, it is okay because you had a cycle in which this was a red path and with this was a vertical edge. So if you replace one edge of this cycle with another edge of this cycle, it should be always okay because you do not add new cycles. So that is exactly what I did in my solution. I made a DFS tree, and if the blue edges form a triangle, then I just take the lowest vertex and replace one of the blue edges with the red edge. And the red edge is just an edge to the parent. I just swap them in the blue and red graphs, and that works pretty well. So problem E. Count the number of almost perfect permutations of length n modulo 998244353. And permutation is called almost perfect if for every I, this holds. So how would one solve this problem? I actually talked a lot during the contest, but I will repeat it briefly. So how can it happen? First of all, it can be exactly 0, and it means that pi equals pi minus first. And it can be if you consider a loop or meeting edges. I don't know how it is called. Meeting arcs, maybe. So cycle of length 1 or length 2. But also it's possible that you have, for example, here 4 and here 5. And this is I. So this is pi minus first, and this is pi. But it is not possible that this cycle is very long, because actually after this one, it should be 4 or 5 or 6. And 4 or 5 are already impossible because you have already seen them. So this can be only 6. And then after that, it can be only 7. And then after that, it can be only 8. And actually, if you walk enough, you will get arbitrarily large numbers. And this is very bad. And the only way to prevent this from happening is just if you have here 4. So this is cycle of length only 4. So this diagonal is with difference 1. So this diagonal is also with difference 1. So you have three types of behavior. 1 cycle, 2 cycle, and 4 cycle with diagonals with little difference. How would you solve this? First of all, I try to find the number. I iterate over all numbers of these cycles. I say that there are k cycles. And after that, I try to find this number. Actually, this is done as follows. First of all, I just consider all these diagonals. Diagonal is just two numbers that are different, that have a difference of 1. So if there are k cycles, then there are two k difference pairs with difference 1. So first of all, I find all ways to choose two k pairs with difference 1. And it was easily proved that there are so many ways of doing it. This is just a mathematical recurrent. You see that this is true when n equals 4k and when k equals 0. And also you see the same recurrent as in these chose numbers, that n over k equals n minus 1 over k minus 1 plus n minus 1 over k. Okay, so this can be done this number of ways. After that, we want to divide these pairs into pairs actually. So there are two k pairs with difference 1, and you want to form k cycles. And you have to multiply this by 2k minus 1 double factorial to do this. It is also a known fact that if you have 2k objects and you want to divide them into k pairs, there are so many ways of doing it. And in the end, we also have to multiply it by 2 to the power of k, because each time if you have a cycle, again, maybe 1, 2, 3, 4, there are two ways of forming a cycle. This way or another in the inverse direction. So also 2 to the power of k, you have to multiply. Well, after these three easy steps, we found the number of ways to choose k for cycles. And after that, we only have to count number of dividing all the remaining vertices into the cycles of length 1 and 2, into arbitrary cycles of length 1 and 2. And this is simple dynamics. So Fn, let's look at what happens with element n. It is either forming a cycle of length 1, or it is paired with some of n minus 1 other elements, and you have to find this. This is easily counted by induction with a simple cycle. And in the end, for example, if this number is g and k, then you just find the sum of g and k times f n minus 4k. And sum from k equals 0 to n over 4. That's it. And finally, the problem F. I don't want to consider problem G and H because they are hard and it is already very late. So in problem F, what actually happened? First of all, you have to read the statement. Okay, I will repeat it. So we have several traffic lights, and each traffic light works like this. It has a certain segment of green light and certain segment of red light. And always the sum of these two segments is t. And all these segments, as you see, are segments on the circle of residues modulo t. So if you have a point on a green segment, then you can just proceed to the next traffic light in time di. And if you are on the red segment, you firstly have to wait till the end of the red segment, and after that you can proceed with number di to the next traffic light. So the first step is to get rid of these di's. So what can we do? Actually, for each traffic light, you know two numbers, this length gi and the number ci, where on this cycle we are right now. So first of all, I say that if you have two traffic lights with distance di, you can think of them as about two traffic lights that are lying in the same point. But actually, this traffic light is its number is increased by di. So ci plus di. Why is that? Because actually there is no difference in these two scenarios. You are here and you come to this traffic light, and when you come there, the number ci is increased by di. So actually you can think of it as it is already in the same point and you have already this number. But actually it is true, and if you, and only if you add this number to your answer in the end. So we of course do it. And after that, it is quite uh, a simple exercise which I failed to do. So you have several red segments, and you want to find the minimum number of time you have to wait. So it is done as follows. Let's, for each point on the circle, store the minimum number that we will have to wait, the number of times that we will have to wait. And we will add the traffic lights from the end to the beginning. So in the beginning, we have no traffic lights, so we don't have to wait in any point. Okay, let's think that we added some traffic light. So if you're in this point, for example, then you don't have to wait. It's just this traffic light is there, but you just pass it because there is green light on this traffic light. So this number is the same as it was before this traffic light. But these numbers, they are changed. Actually, what do you have to do if you are here? You have to wait till the end of this traffic light, and then when you are here, you just have to wait as if you were here in the beginning. So, for example, if this is CL and this is CR, then all numbers CR plus 1, CR plus 2, etc., CL minus 1, and actually CR also, are the same as they were. But numbers on this segment are changed. For example, CR minus first is 1 plus CR, and CR minus second is 1 plus C2 plus CR, etc. So actually, this is assignment of an arithmetic progression on a segment. So on this segment, you now have CR, CR plus 1, CR plus 2, etc. And this is an easy exercise on segment trees. Actually, you have to write an implicit segment tree because the total length of this cycle is t. So I had to write an implicit segment tree, and you saw me doing it, but there were two mistakes that I had in my solution. And because of these two mistakes, I had a wrong answer and I failed to fix it during the contest. So the first mistake was, I guess it was here. See, when I got rid of these t's, actually you have to do two things. You have to add it to answer, and in the end, this addend is added to the answer. And the second thing you have to do is to add this d to the c. But see, I don't work with arbitrary integers. I work with residues modulo t. And when you work with residues modulo t, you have to use some special functions. For example, this function is easy. It just adds these two residues, and if the sum is greater than m, then here you remove m. But see, when I read this number di from the input, it wasn't a residue modulo t, it was just an arbitrary integer. So I made a mistake because I didn't do, I didn't do this in the beginning. So it was just an arbitrary integer, so this function worked wrongly. And because of this, I had a mistake. And the second error was here, I think. I had something like this, but I think it's just an implementation detail, and I shouldn't understand. I shouldn't explain you why it was a wrong solution. Now it is okay. So we have solved this problem. I guess that's it. So thank you for your attention. We had almost a good participation. We lost only 7 rating points, so everything will be okay. Thank you for your attention and good luck.